All right, guys, welcome to Let's Get to the Marks. I'm going through chemical measurements. These questions are for both separate science and combined science students, unless indicated in the question. This is from the fantastic Physics and Maths Tutor website. They got so many packs on there. You might want to grab yourself a pen and paper and a calculator defo and pause the video and have a go at each question and then unpause and watch my explanation. So question one, copper is extracted from metal ores. Oh, by the way, what is this question pack about? This is called chemical measurements. You'll find the link for this in the description if you want to go check out the website. And let's go. Question one, copper is extracted from metal ores. Chalcopyrite is a metal ore containing a compound with the formula CuFeS2. CuFeS2 reacts with oxygen to produce copper 2 sulfate and iron sulfate. Complete the equation for this reaction. You should balance the equation. Now that's worth 2 marks for balancing. You got to come up with the other reactant because there's a blank space and then the coefficient that goes in front of it. And then it asks us calculate the percentage by mass of copper in CuFeS2. And you've been given the relative atomic masses, the ARs down there, sulfur's 32, iron's 56, and copper 63.5. Why don't you pause the video, have a go, and then unpause and I'll go through. Okay, I'm going to go through the explanation. So what we need to do over here is go right. What's been added on, have a look. You can see what's been added on, guys. Look at that letter there. It's not over here, so we know what's got to go there. There's also another big fat clue because if we actually read the question and we use a little highlighter, we can see CuFe2, that's that, reacts with oxygen. So we know our missing compound or molecule or reactant is oxygen. Now we just need to work out how many, like what big number do we need to put in front of there? And we can do that by working out how many oxygens are on the right-hand side of this arrow. So we've got 4 and 4. That means I have 8 oxygens on the right. So I need to, due to the law of the conservation of mass, have 8 oxygens on the left. So I'm going to put a big fat 4 in front, and that's the coefficient I'm going to use there. So 4 times 2 is 8, and that is balanced. That's going to get you 2 awesome marks. Let's get on to the next part of the question. Hopefully you had a go. You'd need your calculator for this. Calculate the percentage by mass of copper. So copper has the symbol Cu. So they're basically asking you how much Cu is in CuFeS2 as a percentage. So what you need to do is Cu, check out the pink. We're going all cool colors here. Right. CuFeS2, maybe not. Cu divided by that times by 100 to put in a percentage, and you've got the marks. You might want to have a go at that now. I'm going to go through it for you. So let's get off the pink. It's a little probably hard to see on the old screen you're looking on. So we want to do 63.5, smash that over the top of this. So I'm going to go another 63.5. And then I'm going to add that to Fe, that's 56. And then that little 2 only applies to the sulfur. It doesn't apply to the iron or the copper. So that is 2 S's. So they're 32 each. So I want to add that to 32 times 2. You could just do that in your head. That's 64. And smash that all together. And we're going to get 63.5. I think that's over 184.5. Hopefully that is right. And let's put that in the old calc and see what we get. 63.5 divided by 184.5 equals times 100, hopefully that's right, 34.417. I'm just going to double check that I've done this right. So, because you know what, I kind of added that up a little bit quick in my head. So let's go 63.5 plus 56 equals 119.5 plus 64. Ooh, no, Tom, you absolute donut. Let me try that again. I think I've mashed that up, guys. Plus 56 plus 64. Always use a calc, folks, or you'll do something like I've done there. So delete. And this is actually 63.5 divided by 183.5. Oh, sometimes you just think you're smarter than you are, don't you? Well, I do. 63.5 divided by the answer. And this is times 100. Thank you very much. 34.604 is my answer. So 34.604. And as that's lower, I'm just going to leave this. Did it say to anything? No, I'm going to go 34.6. Some people might round to 35. They may give you that, but I'm going to 1 dp. And that gets all the marks. That gets all 3 marks. There we go. Let's move on. Don't forget sharing's caring, guys. Make sure you hit the like. I scratch my butt, you scratch my back, I scratch yours. You get the idea, whatever. I don't know what I'm waffling about. Let's get on. Describe a test to show the presence of copper 2 ions in a solution of copper 2 sulfate. So we're looking at what is the test for copper 2 plus ions if you have some copper sulfate. Now, copper sulfate solution, that means say Q. We don't really need to worry about that. But you do need to know these off by heart if you're doing separate science. There are some tests for copper 2 ions. And so this is for separate science only. And one of the tests is called the flame test. Now, specifically, you want to dip a wooden splint, or you can use like a loop and a metal hoop thing, platinum wire. You can dip that into the copper sulfate solution, the CuSO4AQ, and then pass through the non-luminous part of the flame. Don't pass it through the colored bit of a Bunsen burner flame, otherwise you won't see any color. The result you'll get with copper is a green colored flame. So if you do that, you're going to get a green colored flame, and that's going to get you 2 marks. Now, there is another method we can use, because actually you get a green colored flame with some other ions like barium. So sometimes we need to confirm that we're definitely dealing with copper here. And there is another method we can use, and that is we're going to react with, mix with, or add to 10 centimeters of, or whatever you want to say, sodium hydroxide solution. That's what the AQ stands for. And what happens if you do that? Well, you're going to get a blue precipitate. Precipitate. Ah, pitate. Gosh, I hate typing out. What does precipitate mean? Precipitate means solid within a liquid. So you've mixed these two solutions together, CuSO4AQ and NaOHAQ, and suddenly you get this solid appearing out of it. And that will be Cu bracket OH bracket 2. So you'll get a blue precipitate, which is the copper hydroxide solid forming within that solution. And so either go for these two here, or either goes for those two. Right, now I'm going to move on. So looking down the page, copper can be extracted from low-grade ores by bioleaching. Describe what's meant by bioleaching. Grab a pen. What I want you to do now is just write down 2 things that come in your mind when you think of bioleaching. So if you don't know, then what you want to do at the end of this explanation is make a revision card and write what is bioleaching on one side, and on the back, write like 3 or 4 bullet points. And that way you're pretty well armed to attack that question if you get it in the exam. Right, I'm going to go through the answer. So bioleaching is when you get a low grade ore. What's a low grade ore? A low grade ore is a rock that doesn't have a lot of metal in it. So here's my low grade ore. Well, I need to get metal out of that. The problem is with low grade ores, if you do it via normal extraction processes, it costs you more money to get the metal out than you're going to get when you sell the metal. So you're going to go bankrupt. So that's no good. But we have a way we can do it that is sustainable and isn't going to cost us any money. And we just get some bacteria. Check out the loop of DNA and the pili and the flagellum. That's my bacteria. So we take some bacteria, and what bacteria do is bacteria absorb the metal ions. So they will live on the rock and absorb the metal ions. And then what they do, they produce a leachate. Now you might be saying, what the hell is a leachate? A leachate is like a liquid. Okay, so they produce like a liquid, seeps out of their body. Ooh. And in that liquid are our lovely metal like copper ions in the liquid. Now, how do we get the copper ions out the liquid? That's another process. The metal ions can be extracted, and you will get questions that ask you this, from the leachate. And there's 2 ways to extract metal ions from the leachate. And you can do this for how to extract metal ions from the ash that's produced during phyto mining, that you also have to know about. So if you don't know about that, grab your revision guide and make a card on that as well. So the metal ions can be extracted from the leachate using electrolysis or displacement. Displacement would scrap iron, but Anywho, what am I going to write as my answer? So, what two words did you come up with? Well, we're going to, bioleaching is using bacteria um, to form a leachate that contains metal ions. And that is essentially what bioleaching is. Now, if you want to know how to get the metal ions out the leachate, then you're going to use electrolysis or displacement with scrap iron. Okay, let's move on. Zinging down, zinging down, zinging down, zinging, zinging, zinging. Question two. This question is about groups in the periodic table. The elements in group one become more reactive as we go down the group. Rubidium is below potassium in group one. Rubidium and potassium are added to water. Predict one observation you'd see that shows that rubidium is more reactive than potassium. Explain why rubidium is more reactive than potassium. These are very common questions. You need to know them for combined science and separate science. Why don't you grab your pen, grab your paper, press pause, have a go. Okay, I'm going to go through the answer now. If you think about group one, you've got like, oh, geez, let's get rid of the orange color. That was because copper is kind of an orangey color, so I was using that. Right, let's think about the first element in group one is lithium. It's got a little electron in its outer shell. Then what comes next? Then we've got sodium with a little electron in its outer shell. Now you might be going, sir, how am I supposed to remember the order? You got a periodic table in your exam, doofus. Okay, then we got potassium with an electron and rubidium somewhere down here. I can't exactly remember if rubidium's next, but rubidium is below potassium anyway. So what's going to happen? Predict one observation that shows that rubidium is more reactive than potassium. Well, what happens when you add a group one metal to water? Well, I'm going to go through and show you. If you add lithium to water, guess what happens? Um, you get an alkali forming, a hydroxide. You tend to get this when you add any metal to water. Um, Not all metals, but most metals. You get a hydroxide. You also get a hydrogen gas. I'm going to sneeze, folks, so give me one second. Oh, jeez. Okay, yeah, impressive. I sneeze like a girl, but that doesn't matter nowadays. How do girls sneeze? I don't know. That was very sexist. Never mind. Right, lithium plus water goes to lithium hydroxide plus hydrogen. So what we're going to do here, we're going to go, but it's not balanced, is it? I don't know why I'm even balancing this. Why am I even doing this? Who knows? Who can work out the mind? We've got one hydrogen there, two there. So I'm going to smash one there to make four hydrogen. Yeah, okay, that's balanced. Right. Now, we've got the state symbols. I think I tried to do this just to show you that when you add a metal to water, you make an alkali and you give off hydrogen gas. So what would you expect as you go down the group? It tells you that they become more reactive. So how would you expect rubidium, which is more reactive, um, it's going to give off the gas quicker. So you're going to see more fizzing, more bubbles. That was a long way of me saying that. More fizzing, more bubbles. Now, occasionally, because this is an exothermic reaction, guess what? It gives off heat. So you're going to get more heat with rubidium, a higher temperature. Guess what? Occasionally that heat causes the hydrogen to burn. It doesn't really happen with lithium, but sometimes with sodium, if you use enough, you get a yellow flame as the hydrogen catches on fire. And with potassium, you get a violet purpley flame if it catches on fire. And with rubidium, it's even brighter and more intense, higher frequency energy coming out. So I'm going to say brighter flame. Okay, so we've got more fizzing, more bubbles, more heat, brighter flame. They also, these metals are less dense than water, so they float on the water and they get kinetic energy and they zing about. So what I'm going to say is more faster movements on the water. So the metal tends to zing about like a little random movements over the surface of the water, like an ice skater on a pond, and it moves faster as you go down the group. Now we need to explain for this second one for 3 marks. Any one of these points would get you a mark. Explain why rubidium is more reactive than potassium. Check out my diagram, guys. That might have given you a clue. So as we go down the group, we want to say RB is bigger than potassium, right? It's bigger. What does that mean? That means that this electron is further from the center. And what's going on in the center of atoms? Do you remember what the center of an atom is like? It's called the nucleus, and it is positive. And these little electrons are negative. And what this means, if you're further away, you don't feel the attraction to that positive nucleus as much. So we need to put that in words. RB is bigger than K. The outer electron is further from the nucleus. My little e with a minus is my shorthand when I'm typing or writing for electrons. So the outer electron is further from the nucleus, feels less electrostatic force of, you can just say it's less attracted. You don't have to use these fancy words. They will be on the mark scheme, just less force of attraction or weaker force of attraction. So the outer electrons further from the nucleus feels less electrostatic force of attraction to positive or oppositely charged nucleus. Then I don't have to explain the charges. Oppositely charged nucleus. Okay, so what does that mean? That means less, I'm going big on this, less energy is needed to remove the electron, so it reacts more easily or loses electron more easily. Okay, so I've kind of done a 4 marker. So your kind of clear points are that, look, as you go down, they get bigger and the electrons further from the nucleus. This means the electron is less attracted to the nucleus, so it's easier to remove because it requires less energy. So lots of points there. There is a point that's always bonus and is really an A-level point, and that is that as you go down the group, you get more shells of electrons. Now, why does that matter? These shells of electrons shield that positive charge from the negative charge. They even, because these are negative, they even repel that electron further away, making it even easier to take away. So the fact that rubidium has more of these shells means that that electron is even easier to remove. And instead of having to write all of that down, which would be a whole paragraph, in A-level chemistry, we use the term shielding, and this is always on the except in GCSE as well. So we can say that RB has more shielding, and that will get you a mark. And really, that shielding is just describing there are more shells. You wouldn't have to go and do this explanation, but more energy shells block the attraction to nucleus. They don't really block it. They repel the outer electron further away. It's more complicated than all of that. So you can just say more shielding and get a mark for that as well. Now, of course, you can't have 6 marks for this answer. You've got to only take 3, but there we go. Let's move on. Okay, looking at C, I see. Ha ha ha. Complete the equation for the reaction of rubidium with water. You should balance the equation Rb plus H2O. I just did this, so if you can't remember it, you are forgetful. So what we're going to do is grab your pen, grab your paper, pause the video, have a go. Now, I'm not sure if you need state symbols. Normally when it's 3 marks, you need the state symbols, but they haven't mentioned that here. So I think they're giving you 1 mark for each reactant and then 1 mark for balancing. Let's go. Rb plus H2O. Anytime you add a metal to water, at GCSE, you just have to know about the alkali metals. You don't really have to know about group 2, but you're going to make a hydroxide. Now, if this was group two, for instance, magnesium, the hydroxide formula would be different. It would be OH with a little 2 there because they're negative, and you need 2 minuses to go with a 2 plus group 2. But it's not group 2, it's group 1, so I'm going to shut up and get on. So there we go. That's going to get you your first mark. Now I'm going to put the state symbols in, but you don't need the state symbols for this question. But you know what? If you don't know them, get to know because you have to know them. So there's your first mark for rubidium hydroxide. Now I'm going to put, oh, geez, that's a small space. They expected me to do that. Okay. Let me just select this and move this over. Normally it will appear. Let's do it. I'm going to put this. Oh gosh, that's no good. I'm going to put that there over there plus because they didn't leave enough space on their exam paper because they're idiots. So you're going to get rubidium hydroxide and then you're going to get hydrogen, and hydrogen comes off as a gas. Then you need to balance. You have to know this equation off by heart, by the way, peeps. So that would get you 2 marks, 1 for each reactant. And then we need to balance. Now there's 1, 2, 3 hydrogens on the right. Conservation of mass means I need 3 over here, but because that's an even number, that's going to be hard. So your best bet is to make the hydrogens even on the right. Then it's really easy to just put a multiplier, a coefficient here. So what I'm going to do, folksy folks, is put a big fat 2 in front of this, and that makes 2 H's. Plus 2 H's is 4. So I just need to put a big fat 2 there and make 4 H's. Problem is that when I put this big fat 2 here, I also made 2 RBs, but luckily RB's on its own. So we just put a little 2 there and we're solved. Boom. We've balanced it correctly. There we go. All right, let's move on. Keep moving on, keep moving on. Woo! Noble gases are in group zero, which is a correct statement about the noble gases. Tick one box. The noble gases all have atoms with 8 electrons in their outer shell. This is not true. If you look at helium, helium has mass number 4, atomic number 2. So it's only got 2 electrons in its outer shell. It's a true statement to say that noble gases have full outer shells because the inner shell only needs 2, but we can't say they have 8 in their outer shell, even though in some periodic tables they call it group 8. Anywho, noble gases have boiling points that increase down the group. Now, this is true, and this is our correct answer. And why is that? Well, if you take 2 helium atoms, they have something between them called an intermolecular force, not a bond, because noble gases don't really form bonds easily, as they've got full outer shells. But this dashed line represents a weak kind of intermolecular force, but these aren't molecules, so it's a weak interatomic force, whatever. Yeah, so these are weak forces. The bigger the atom gets, so say we looked at argon, which is further down the group, has a bigger mass number. If we look at argon, it is going to have stronger forces, and that is why the boiling point increases. Now, this happens to all non-metals. So let's say I was looking at group 6, or I was looking at group 5, or I was looking at group 7. Now, you do group 7, they're the halogens. So if we looked at fluorine, fluorine is diatomic. Remember, it comes as 2s. You need to know this as well. This is in group 7. If you look at fluorine, the 2 fluorine atoms are bonded together, but there are weak forces that hold the 2 fluorine molecules together, and that's what we need to overcome if we want to turn it into a gas. Now, if we look at chlorine, chlorine is bigger, and so the forces between 2 chlorine molecules are going to be stronger. And that means as you go down group 7, the boiling point increases because you need more energy to break the forces between the molecules. As you go down group 0, same thing, but you're dealing with they're monatomic, they're atoms, but you need to they get bigger, they have stronger forces essentially. And that's for all non-metals. So for group 5, 6, 7, and 0, as you go down the groups, their boiling points increase. And you can just remember that as a rule for non-metals, and it's because the forces between the particles get stronger. Okay, enough whiffle waffle, whiffle waffle waffle. Let's go. And these other two are wrong. The noble gases have molecules with 2 atoms. That would mean they are diatomic. That is group 5, 6, and 7 are all diatomic, or yeah, we won't go into that. Group 0 is monatomic, so they're not. The noble gases react with metals to form ionic compounds. No, they don't react. They have a full outer shell. So anyway, those last two were wrong. I'm going to stop waffling and do the last question. This is the last question of this little paper. Make sure you hit the like and you help a poor broadcast teacher out. Right, here we go. The table shows 3 isotopes of neon. So we've got the mass number, we've got the percentage abundance over here. What you need to do is work out the sum of the mass number times the abundance and divide by the total abundance. Why don't you have a go? All right, I'm going to go through the answers. So what you're going to do, you're going to go 20 times 90.48. You're going to bracket that, and you're going to add that. I haven't really got space, so I'm doing it like this. I mean, this isn't the best way to set it out. Times 0.27. And then you're going to add that to 22 times 9.25. And you're going to sum all of that up. So I want to boom, sum all of that up and then divide by 100, because if you add all of these up, they add up to 100. And that is going to give me an answer. And I'm going to work that out right now. So let's go 20 times 90.48. You should get 1,809.6. So that is 1,809.6. And I'm going to add that to 21 times 0.27, and I get 5.67. And then I want to add that to 22 times 9.25, and I get 203.5. Now we want to sum all of them bad man together and then divide by 100. So what's that going to equal? Let's go plus 1809.6 equals that, plus 5.67 equals that. And what I got, I don't know if you got the same thing, I got 2018.77, 2018.77. We've got to divide by 100. We can't leave like that. That can't be the average between 20 and 22. So, and the answer I get when I divide this by 100 is 20.1877. Now we're going to do a common sense check. Common sense check means you use your common sense. Really, we're working out the average of these masses. If I get something like 50, how can 50 be the average of something that's 20, 21, and 22? Can't be the mean, right? So you'd expect something like 21. There's more. Imagine you have 20 people, three people, you have 100 people in a room and 90 of them weigh 20 and 22 of them weigh 9. What would you expect the weight to be? You'd expect it to be closer to 20. Look, I've got 90.48 20s. I'm expecting the overall average to be closer to 20, and that's what we got. So we know we've done it right. This has got us 2 marks, but it's 3 sig fig. What does that mean? Starting from the left, ignoring any zeros before the decimal, and we don't have any zeros. We don't have a decimal at the start, so we don't have to ignore any of them. Starting from the left, include the first 3 figures. So 20.1. However, as the 8 is greater than 4, like, so if you go into 5, 6, 7, 8, or 9, you're going to push that up to 2. So we're going to represent that as 20.2, and that is going to get you the last of the marks. All right, guys, hope you found that helpful. Don't forget to check out the fantastic Physics and Maths Tutor website. Has loads of packs like this. Check the link in the description for it. Don't forget sharing's caring. Hit the like, punch up the bell, subscribe. Let's get to the marks. I'll catch you lot on the next video.
You're still here? It's over.